Yeah, so KNearest Neighbors, section 33, our first, section of this module for machine learning, which I think I mentioned this before. I think this module, people tend to like this module a lot because, you're doing machine learning, the cool stuff, I like to say. It's all very cool, but, we know what's really the coolest stuff. But anyway, I think it's kind of exciting because there's a lot of prediction modeling stuff. And I think a lot of the things that I've kind of mentioned in the past about, what's it called? Like, oh, these are things that we're going to do later on, kind of thing. These are things you have to consider, like we're going to look more into this in the future. That's what this module really is. It's like, this is kind of the time where we talk a lot about this stuff that I kind of like mentioned in the past, like, well, don't worry about it right now, but it is something you have to worry about in the future. Okay. So I think it's pretty exciting. All right, so I'm going to start sharing my screen. And like always, that fork is there with all the resources. Sharing my screen. And then, oh, there you guys go. Oh, I think I figured out how, okay. I actually think I figured out why my Zoom windows move around. It's the window I'm not expecting to adjust. We'll see if that's true next time. But yeah, no, if again, like I kind of keep mentioning this just because I've been making some changes. This past week, I haven't made too many changes, but going through, if you go through like the machine learning resource, I might be updating this throughout the week and next couple of weeks. So just kind of know, it's like, I kind of frequently this refresh your fork and all that if you're using it. Okay, so first thing we're going to talk about is distance metrics. So the reason why we're going to talk about this first, minimize you, there we go. Okay, the reason why we talk about this first is basically KNearest Neighbors, and a few of the next, for the next week, we're going to be talking about supervised learning classifications. And so we kind of mentioned a little bit before about supervised learning. What do you guys remember about supervised learning? Does anyone know why it's called supervised?
Because the data has to be labeled.
That's right, yeah. We have to know what we're looking for, essentially. That's the supervised part. Versus something we'll talk about, I think next week is when we'll mention it, is something called unsupervised learning, where essentially no one really knows what the labels are. This is actually really useful for things like, let's see here, like identifying different groups where you're not really sure, like you have a group of people, like, and let's say the classic is like movies, and like, oh, like what kind of moviegoers there are. It's like, well, you could try to label, oh, these are these kind of people, like, like, oh, these are like people who love horror movies, but like, there's not really clear, like, well, what group is that really? You can say, okay, computer, basically find out which group belongs to which. That would be closer to unsupervised learning, where you might not have a firm, like, what the order is. This is actually really useful for marketing too, where essentially you're like, hey, I have a whole bunch of people. We like to reach out to these different people, but we don't really know like how to classify or group them together. We could try, but we're not really sure what would make them like specific to this group. You can use unsupervised learning to do that kind of stuff. But supervised learning, which we'll focus on this week, is essentially you have a bunch of training examples, and your training basically comes to the fact that you have some properties, some features, right, of like whatever data points you're looking at, and you say, okay, these are all the properties, and this is what the label should be. And you train on saying, okay, these are the properties. Based on the properties, what label should they be? And then when you actually go to test it out and deploy it out, you'd say, okay, I have these same properties, but I don't know what the label is. This is what likely it is. So it's prediction. And again, classification. A lot of these, this one, not so much, but some of the algorithms mostly will be focusing on classification, mostly because it's like, that's typically how they're used and probably the most understandable. But some of these algorithms can also be used for regression. So basically use those parts to kind of like linear regression, where we're having something, a continued, not a class, like logistic, but instead something that's kind of like a continuous variable, or something that can be more than one, like not more than one class, but like it's a spectrum essentially. So you can think of like in the housing project that we had for the first, was it module 1? That was a regression thing, but we could slightly change that to be a classification if we had something like low price, high price, medium price. That would be like a classification. Okay, cool. So, but to distance metrics then, right? Like, how does this work? So with distance metrics, what we're going to do for KNearest Neighbors is basically use that to measure how close things are. So we need to know how close things are, which seems like a really like simple thing to do, but it actually turns out there's a lot of ways we can measure things out. So it's actually worth us going through at least the most common ones. And I'll mention at the very end about like a couple other things too, that maybe the curriculum didn't mention. But basically, the idea here is that if we have 2 points, so I just made this little code here. This is just for us to plot. I kind of kept this separate versus like putting it all together, just because I think it's kind of nice for you guys to see how this 3D plots. It's a little bit different from like what you might normally do. But basically I have 2 points here. So this is in 3 dimensions. So this is like, you imagine X, Y, and Z. So on the X-axis is 2, -3, 5, and 1, 1, 3. I'm just putting it all together. And all this stuff is just to go ahead and plot this out. I won't walk through it completely. So I just made them 2 different points. You can see here, this is my little point here. This is my little point here. A little small, but we get the point, right? So we can see it's like, okay, like basically for K-nearest neighbors, we have to know how far away are different points from each other. And the thing is that like, well, there's a few ways we can measure this, okay? I think most instinctively, people would probably say, we'll just like imagine drawing a line from here to here, or like a straight, arrow. It's like, oh, that's how far they are. But you can imagine like, let's say not in a scenario, like if you were talking about how far you are, like on Google Maps, right? Or, like Apple Maps or whatever you use like to like figure out how far you are. You wouldn't really measure like the distance from like that one point to like the other city. If there's like a big, lake in the middle of the way, well, yeah, technically they're that far away. In some way you can measure, but really it makes more sense to measure out going around that lake. So you can now imagine there's a few ways we can measure distance. So you can imagine here, we can even talk about like, if let's like pretend like these 2 points, there's like a building in the middle, we can like maybe walk around it and go that way. So it's not a direct flight path. So that's going to be similar to how we would do a Manhattan distance. So Manhattan distance, and this is just from the curriculum, you'll probably see something similar to this if you search for Manhattan distance. But basically is, you can imagine just a grid. And I like to kind of compare this to like city blocks. If you imagine this as point A and point B, and you're like a nice, like let's say New York where it has like nice like grid patterns, right? Essentially you say, okay, well I can go up this many, so I go up 1, 2, 3, 4, 5. Oops. Let's turn that off. Got my little Google Home thing here. So here, we'd like go up by 1, 2, 3, 4, 5, 6 blocks, and then 1, 2, 3, 4, 5, 6 blocks to the right or east or whatever, right? And that would be like, oh, we're a total of 12 blocks away. What's nice about this, as long as you use the same, like the blocks are all the same size, you can go up 1, east 1, north 1, east 1, and that will still be 12 blocks away. It doesn't really matter how you travel on the grid. It's just saying, oh, how far you are from, or how many blocks you have to walk. So it's really nice that basically you can say, okay, if this is my first axis, this is like my y-axis, this is my x-axis. I can just say how far are they in the x-axis, how far are they in the y-axis. And basically that would be add those together and get my distance. Note this green line here. This green line would not be the Manhattan distance, right? This actually we'll talk about as being the Euclidean distance, or you think back like Pythagorean theorem, kind of that idea. I also kind of mentioned that, well, we'll talk about this in a second. But anyway, just know that it's a comparison. Note that kind of looking ahead, what's going to be shorter, the green path or let's say like the red path up here?
The green.
Yeah, the green, right? So we'll see this pattern as we kind of go into like other distances metrics. We'll see this actually gets, the higher order distance will actually get smaller and smaller. It'll always be smaller. So we'll see what that looks like in a second. But anyway, Manhattan distance, pretty simple. So the way we can write this out like as a formula is just saying the distance between A and B. It's just saying that these A sub k and B sub k, those are basically saying like, the X component or the Y component. And you can do this for, note that I put this K here, this N represents how many dimensions. So if we're looking at just 2 dimensions, we'd only look at A sub 1 and A sub 2 and B sub 1 and B sub 2. If we had 3 or 4 or 5 dimensions, then we would have to consider, going through all the part and add up those distances between those different axes. Note, I think this sometimes throws people off, but when I say dimension, I really just mean direction, or in this case, really just mean features. So when I say there's a new feature, that means a new dimension. Okay, sound good so far? All right, awesome. So kind of see how we code this up. I'm using that same AB just to kind of, I'm gonna try to keep that consistent so we kind of get an idea of like how this distance is. But I'm using 3 dimensions, so 2 minus 3, 5, 1, 1, 3, and just to show you guys, that's my point. So remember this is describing like a single point. So the first thing I can do is take the differences from A minus B. Since this is using NumPy arrays, it will basically broadcast across. So I can do 2 minus 1, minus 3 minus 1, minus 5, or sorry, 5 minus 3. And you can see here, I got the differences in an array. So you can see here, 1, minus 4, 2. Okay, makes sense so far. And note that this minus, you might be like, oh, like why is it, what's a negative distance? We're gonna take the absolute value anyway. So it's gonna basically be 4. Basically, if I swap another way, it'd be negative for these 2 and not this one. All right, so then, like I said, take absolute value. So now you see 1, 4, 2, and then just sum them all together, and we get a distance of 7. So that means it's on the Manhattan distance is a distance of 7 units away. Okay, make enough sense? Awesome. All right, so then we get to something a little more familiar called the Euclidean distance, Pythagorean distance. This is, like I said, like Pythagorean theorem. I kind of like, if you kind of imagine this like, you know, walking down blocks, this is like as the crow flies. I wrote it here because I kept messing up the saying. I couldn't remember exactly how to say it. But like you can imagine like, oh, okay, this is like the minimum distance what we usually think about like, when we're talking about like traveling like on a map. Not considering, I just realized, not considering the curvature of the Earth or whatnot, but the idea is here, okay? So the way this formula is going to look very similar to what we had before. So remember, our before basically take the absolute value difference and sum them together. This one, we're taking our squared difference. So so let's say the x component minus the x component for b, square it, and then add up that all together, and then at the very end, take the square root of it. Okay, so basically this square root is gonna, you guys know the Pythagorean theorem, but like basically it's gonna lower it down. And note again that this is for any dimension, not just 2 or 3 dimensions. It can be 4, 5, 6, 100 features. That's all the same thing. Okay, cool. All right, so coding your distance look very similar. I'm using those same exact, should be the same exact numbers. Oh, I think I actually switched -1 and -3. I'm gonna switch this back. I think that's right. I just wanna make sure it's the same values, yeah. I don't think that would matter in this case, but I'm not gonna take any chances. Okay, so to have those points, we take our differences like before, but this time we square those, so these would all be positive. Okay, we sum them all together, okay, and we take the square root. And we get here, the distance is 4.58. So note that the distance for the Manhattan distance was 7, right? And the Euclidean distance will be 4.58. So note that the Manhattan distance will always be at least, or will always be at most the same size as the Euclidean distance. Does anyone know like what special case it would be where they're the same size? It's when they're on top of each other. So basically a distance of 0. But at most it'll be the same size. Otherwise it'll be less. Euclidean distance will be smaller than our Manhattan distance. I think that makes most sense, like, right? Like the most distance would take, you know, when we go, like it would take longer to move each block versus if you were like a crow, right? A bird that can fly directly to there. Okay, cool, all makes sense so far? All right, then we get the fun stuff, the Minkowski distance. So the Minkowski distance kind of assumes first that we're in a normed vector space, which basically means is that the vector space is still perpendicular. It's also of unit length. So basically a typical what you would expect of like a vector space. That's kind of like a special kind of condition, but it's usually kind of assumed. It's not usually a big issue. But what's kind of cool is that Euclidean distance and Manhattan distance are basically Minkowski distances. There's just a special case of those two. So basically you can kind of see here on our original formula, we had a squared and then we took the square root. We had over in this case, the absolute value, we didn't have to do any like square root or anything like that. You could technically say we did the first root, because the first root, it would be literally like to the power of 1 over 1, which would basically be 1. So that's kind of what was going on here. And that's kind of like what happens with Minkowski, is that we say, okay, the distance is going to be from A to B, and we're going to take that sum of the absolute differences raised to some power C. So C is some number, right? It could be 1, 2, 3, 100. It could be whatever that value is. And then we're going to sum those all together, and then we're going to take the Cth root. So note that if you remember back, like writing in algebra, 1 over C raised to the power is the same thing as taking the root, the Cth or whatever root you're taking. Does that make sense? Okay. So one thing kind of note is that we can kind of do this to compare it with other distance metrics. So you kind of probably got the feel for like how I do the absolute differences, the power differences, raise it to the power C, right? The sum differences, and then add them all together, right? And I'm sorry, add them up all together, and then take the Cth root. Okay, makes sense. So you can see a little function right here, which is nice and convenient. Okay, so I'm just going to quickly just show you a little bit comparison. So we see the Manhattan distance, just C is equal to 1, and we should get 7 in this case. Sure enough, we get 7. Okay, if we do Euclidean distance, I think it was like 4.58, and sure enough, we get 4.58, right? And so Minkowski distance, let's say we do a higher order like 5, so C is equal to 5. What do you guys expect? Do you expect this number to be bigger or smaller than the Euclidean distance? It's not certain, but at least based on what we're seeing so far, Manhattan distance is like order 1, order 2 is smaller. What would probably be like the next order down? Let's say like order 3. Probably smaller than that, right? Yeah, so let's try that. So we can see 4.179. You can see that, okay. And then, for example, if I went back to my original 5, you can see 4.02. Turns out I can actually go even smaller, like 50, right? And you'll see that we basically start approaching this values and stuff like this. We get smaller and smaller. Actually, I don't know. I think at a certain point, I'm going to actually get, Python will start rounding because it's such a high number. I think, for example, this will only be 1. Yeah, it'll stay at 1 because I basically reached the limit. But if you were to kind of keep plotting this down, the numbers would get smaller and smaller and smaller and approach, I think, to the point of just essentially 0. They have that right. Essentially, they're pretty, like at a certain point when you're measuring distance, they're basically right next to each other. Okay. Cool. All right. So anyway, that is Minkowski distance. Just to kind of show you a little bit what this looks like too for the different numbers. So I put some extra random numbers here. We can see the Minkowski, the Manhattan, and then the Euclidean, and then higher orders like the 5th Minkowski. Okay. Any questions on this formula? Either Minkowski, Euclidean, or Manhattan.
When would you use like a higher order than like 2?
Yeah, so this is a good question. And the main thing is basically it depends on what you're doing. And for the case of K-Nearest Neighbors, basically it just tends to be that Euclidean distance tends to be one of the best ones. And essentially what this is trying to do, it's punishing, not punishing, it's really emphasizing when something's really far apart, it's going to raise that to a power, like a higher power, and that's going to make it really emphasize that it's even further apart. But then that root power will squeeze it back in. And it's supposed to represent a little bit of like, if you consider more dimensions, essentially more degrees of freedom. This is getting very mathematics, to be honest. But basically what the best thing to do is see what performs well, if that makes sense. And what's nice is that people have done this in the past, and usually Manhattan or usually Euclidean distance is the best metric for K-Nearest Neighbors. There's other distance metrics. So this kind of actually leads right into like the notes metrics, scalar metrics. There are things, for example, like the Jacquard distance, which is really useful for understanding where like objects are and stuff like this. There's also things called Cosine Similarity, which usually is not very good with K-Nearest Neighbors, but it's useful for a lot of other ones where we're measuring distance of like how far apart things are in multidimensional space. So for example, kind of going off like, this is like a very small subset, like Minkowski is like a very small sliver of all the different metrics you can use. But I'll just briefly say cosine similarity because it is a very common thing that we'll see like in other algorithms. It's not useful for sklearn or K-Nearest Neighbors, but I think it's important to kind of know. If you have, I'm going to just draw on here. So if you imagine you have like your 3-dimensional plane. Oh, I know, I can actually use my 3-dimensional plane. Look at that. Okay. If you imagine you have your 3-dimensional plane here and you have start from the origin, which, and whatever, I'll just pretend this is the origin. It doesn't really matter. Okay. And this is pointing, oops, I gotta draw. Like you have a vector that goes from here to here. So it's a straight line, right? And there's another one that points from here to here. What cosine similarity basically says, okay, if you drew like a plane, which I'm not going to be able to draw very well, I don't know if I should try, but if you imagine you drew like a piece of paper, so it's kind of like sideways, and so those 2 arrows are perfectly flat on this flat plane, right? The angle, so this is like the center right here, this angle on that piece of paper, that would be the cosine similarity. Basically use that to say how close are they together. And this is really useful because you can always do this for any 2 vectors in any dimensional space. So it means that you can always have that distance, and it's actually really useful when we talk about, what's the one that we're going to talk about in the future? Sorry, I'm trying to think real quick. Oh, sorry, I guess we're going to talk about that in mod 6, but like something with like embeddings and stuff where you essentially map words to a higher dimensional space, and you can actually use that similarity to know how close are these words together. So cosine similarity is really a useful kind of thing. But anyway, it doesn't work well for k-nearest neighbors, so we're going to kind of skip over that right now. Okay. A good question on like when you would use this, because I don't think it's not intuitive of like when would be the right time to use this. And basically a lot of this stuff for machine learning ends up being, hey, like check it out, see what classically does well, and see how it performs. And it really just depends on the data set. But here is the distance metric. So you can see we'll actually use this for k-nearest neighbors, but they already have a few ones. For example, Euclidean distance, Manhattan distance. You can probably see Minkowski right here. And you see Minkowski will basically will go to either Manhattan or Euclidean if you change the distance. But you can see there's a whole bunch of other ones, for example, that we have that we could possibly use. I think I mentioned, is Jacquard in here? Yeah, Jacquard's here. So that's common here too. So these are a little bit different. These are more for like if you're detecting like where an object is, to know like, you know, for example, if your object is like right here, but you said it's like right here, so there's some overlap but not quite right, how do you measure that? Jacquard would be something similar, along with all these other great metrics that you can do for measuring how far something is. But for at least for k-nearest neighbors, Minkowski is pretty like much the default, like, and usually Minkowski meaning like the Euclidean distance. Okay, cool. So I just wanted to put that note since that does exist here. All right, yeah, so that's distances. Do you guys have any questions about this overall? Else? Okay, cool. So let's go to k-nearest neighbors.